almost at the end of our talking about capacitors. Physical properties, what makes capacitors work the way they do. We'll look at three types: parallel plate, cylindrical, and spherical. There's two basic things: how far the plates are apart from each other and how much overlapping area. And so we want to get into those details. The most basic capacitor we think about is a parallel plate, two isolated plates. The simplest would just be separate them by air or a vacuum, connected to opposite terminals of the battery. And that's where our sort of symbol comes from for those. When you charge them up, you have positive charge on one side, negative charge on the other. You get a relatively uniform electric field in the middle. The closer together they are, the more uniform that is, and the less those edge effects matter. We tend to imagine that they are perfectly uniform electric fields inside for the purposes of our calculations. So how does the capacitance depend on the physical properties of this, right? Obviously, you've got two plates. They have a size. They have a separation distance. And that is the stuff that we want to look at. So the way we're going to figure this out is we're going to use Gauss's law to figure out the electric field between the plates. And we'll use the voltage formula that relates the electric field and the distance to each other, to the potential. And then we'll use our capacitance formula, which is defined as capacitance is equal to Q over delta V. That is the definition of capacitance, right? How much charge can you store for a given voltage or a given volt of potential? And we're going to put all three of those pieces together to try to answer these questions. So you can follow along, page 42 in your packet. I believe these page numbers are correct, I hope. The plates have some area and spacing, right? So we can think about the way Gauss's law works, right? We have some electric field going from sort of left to right here. We create a Gaussian cylinder. There's an electric field inside. And of course, if these are infinite parallel plates, there's no electric field on the outside, right? The end cap area is a different area, that A prime, than the area of the plates. We're not worried about that right now. So what we have from Gauss's law, right, we only have the electric field going through one end, since again, outside of parallel plates, we say that the electric field is zero. We have a sigma Q divided by A, where that A is the total area of the plate. And we end up with a uniform electric field, Q over epsilon naught times the area. Now, that exact value may be something you want to think about and remember, but right now we want to apply it. We're going to use the fact that you can find the voltage from one plate to another by knowing the separation D, that distance, and using this formula, E dot ds, E dot dr, whatever formula we're going to use. The electric field is a constant, very nice, right? And for uniform fields or constant fields, we don't have to worry about E dot dr. We can just say, well, it's negative electric field strength times that distance D. And so we can say that our potential is negative QD over epsilon naught A, where Q is the charge on the plates, A is the area of the plates, epsilon naught is our constant, and D is that plate separation. So we're using an absolute value here because we're really only interested in how much voltage there is, not exactly which plate is positive and which plate is negative. One more step, we know that C equals Q divided by V. So if we do that, we have Q divided by, QD over epsilon naught A. We get epsilon naught A over D. And so we say that the physical parameters that affect the capacitance are the epsilon naught, the sort of stuff having to do with the fact that there's a vacuum or air in between the plate, the area of the plates, and the distance of their separation. So what does this really make sense? Yes, we think it does, because if you increase the area of overlap, there's more space to store charge, so you get bigger capacitance. As the separation distance gets smaller, the attraction between the plates gets bigger, right? So it's easier to put more charge on there if you bring them close together and you get a bigger capacitance. So that's the basic idea. The closer together the plates are and the bigger the plates are, the more capacitance you have. Now, that was with a parallel plate capacitor, but we can do the same thing with a cylindrical capacitor. Imagine a ball of metal surrounded by a spherical shell. We're just cutting right through them to get that. We'll charge the inside up positive, the outside up negative, and you've got this radially outward electric field. We have radius A and B for the two different radii that we care about. We're going to draw a Gaussian surface surrounding just the inner charge, and we can do the same thing. with either spherical or this is a cylindrical, so it's a wire with a cylindrical shell looking something like this. This is a different kind of perspective on it. We can still do Gauss's law. There's the Gaussian surface, right? We've already solved this problem. 2 pi r L is the area of the lateral surface area. The electric field should be constant everywhere on that surface, and that's Q over epsilon naught. For Q enclosed, and that Q, right, in this case is all the Q from our capacitor. We know that the electric field depends on 1 over R with a bunch of constants in front of it. We can use our voltage formula. We now can't just use the uniform field formula. We have to use this electric field formula, so we're going to integrate from A to B. So we end up with a natural log formula there. Sorry, jumped ahead. That's the delta V. And so we can go ahead and put that together and say C equals Q over delta V, where there's our delta V, our voltage across it. And we end up with this formula, which may or may not be obvious to you. But certainly, if you think about this formula, you can ask yourself, does it make sense, right? As the length gets longer, right, you get more overlapping area in a sense. We get a bigger capacitance. As A gets closer to B, right, the separation distance between the two layers gets smaller, then the natural log of B over A gets really, really small. And the smaller the denominator goes, the bigger the capacitance. So essentially, the same thing is true of this as of the parallel plate. The closer the two conductors are, the bigger the capacitance, and the more overlapping area, the bigger the capacitance as well. So those two have a lot in common, even though there is this natural log in there. The last one is the spherical capacitor, where we can do the same thing. We've already solved the problem where we do the Gaussian surface, and we find out that it's a 1 over r squared relationship for the electric field. So that's an answer we've done before. We can find the potential difference between the two plates. E dot dr, the integral of that. We have the electric field, integrate from A to B, simplify that down as much as possible. And so you get something that's a little bit more complicated, and we'll resolve that in a moment. We can put it into the capacitor formula, right? We end up with this for our capacitance. And again, we want to check and see if it makes sense. The bigger A and B are, the more overlapping area, right? If you get a really, really big cylinder and you wrap around it a pretty big, spherical shell, you'll get more capacitance than if you do a really tiny one with very little overlapping area. But there is this other piece. As A and B get closer together, right? B minus A gets very, very small, and that's in the denominator. So as the difference between A and B gets smaller, so too does capacitance grow. So the bigger they both are, and the smaller the gap between them, the bigger the capacitance. So again, fitting in with what we know from a parallel plate and a cylindrical capacitor. So what do we know? Parallel plate capacitors, cylindrical capacitors, spherical capacitors. They all have these relationships. The big idea is the more overlapping area of the two plates, the bigger the capacitance. And the closer together those plates can be, the bigger the capacitance as well. Now, all of these assume a vacuum or air, essentially. That's the epsilon naught piece. But you don't have to fill a capacitor with a vacuum or air. In fact, it's actually kind of hard to maintain a capacitor with an air gap. You can only bring it so close before, minor vibrations might bump them into each other. So instead, we often put an insulator inside. Sometimes it's just paper, sometimes it's cloth, sometimes it's paper or cloth type material saturated in some other solution. Oftentimes capacitors kind of have a liquid inside. If you cut them open, they start to ooze. And that's because of that. And so what we do is we essentially add this extra constant in there. This is a kappa, but it doesn't really matter that much. All that does is it adds an extra factor with the dielectric constant. And there's like so many of these constants, like the friction coefficient and other things like drag coefficient, all these kinds of things are things you have to experimentally determine for a given material, but they are things that you can figure out, and it will always be greater than 1. It will increase the capacitance of a capacitor. So here's how they work. If you have a capacitor, we'll just use a parallel plate because it's the simplest one. And you think about the electric field across it, we have some situation where we've got a particular capacitance. If you insert a dielectric material, a dielectric is an insulator, which means charge can't actually flow. But what does happen is that the presence of an electric field will make the individual molecules or atoms become polarized. Their electrons will spend a little more time in that probability cloud closer to the positive charge, and the other side will become correspondingly slightly positive. So this will be a polarized material. And so what this does is it induces sort of a charge that actually helps it hold more charge. And how is this the case? Well, if you look at one side, right, the negative plate, well, suddenly you've got positive charge really close to it, charge that can't jump onto it and recombine. So it's actually easier to put more negative charge on there, and capacitance will increase. There's a bunch of different dielectric constants. They're not terribly important for you to know, except that air is about 1, and a vacuum, a little bit more, but a vacuum is also 1. That's why we don't have to bother with the kappa if it's an air gap, but everything else has something in there. This strontium titanate, or whatever that is called, that's something that we use in capacitors a lot. That's why it's on there. It's got a really high dielectric constant. It turns out that if it's a polar compound to begin with, like water even, although water can be tricky because it can be a conductor, have higher dielectric constants. So the last sort of thing to think about is, what if you were to have a capacitor and add a dielectric to it? Well, if it was connected to a battery with a given voltage, putting in the dielectric means that you've increased the capacitance, which means you have allowed more charge to flow on that with a given voltage. Right? The voltage of the capacitor stays the same because it's a constant voltage connected to a battery. The capacitance increases, and so then the charge stored can increase. Right? Hopefully that makes some sense. But if you charge up a capacitor, just wire it up to a voltmeter, right? And then you insert a dielectric that's isolated, you can't change anything. Well, the thing that's constant this time is the amount of charge you placed on it. What changes is the capacitance. Capacitance goes up. And since Q equals CV, or V equals Q divided by C, a bigger C with the same Q means the voltage will actually drop. Kind of interesting. Voltage of the capacitor will decrease. So it all depends on what you're holding constant, and we know adding a dielectric will increase the capacitance, and then we see what happens in that case. So why does this actually happen? Why does the voltage decrease for an isolated capacitor? So we'll go back to this diagram here. Basically, the electric field between the plates is reduced. And how is that? Well, notice the electric field is going from positive to negative, from left to right in this picture. And that means that if you place something inside of it that is polarized, where there'd be a bunch of little electric fields going the opposite direction, right? It's going to make it a little bit weaker in there. So the electric field is reduced, and therefore, because voltage depends on the electric field strength, the voltage will actually drop as well. So if a capacitor has a dielectric, we replace epsilon naught with kappa times epsilon naught. But that's actually true for things like Coulomb's law as well, right? If you're calculating Coulomb's law for two charged particles, a force between them out in space, if you put them not out in space but inside of a ball of plastic or something like that, then you need to replace epsilon naught with kappa epsilon naught to actually find out what the force between them is, because it will change that value. And since epsilon naught is in the denominator and the dielectric constant is 1 or bigger, this will actually reduce the electric force, just like it reduced the electric field strength inside of that capacitor. Right, if you were to take these two charges and put them in water, for example, right, if you replace that with, 80 for the capacitance, right, they will not pull on each other as hard. It will be a weaker electric force. All right, so that's kind of the basics of the physical stuff going on inside of a capacitor.